Hi, it's Mr. Benson here. I'm going to work through the 2011 motion questions. This is questions 1 to 6, I think. And I'll just work through how I would get the answer to each of these, which shouldn't take too long. I might split this into 2 videos if they get too long. Okay, so before we get into it, I just want to show you something that's quite an important document. You need to be familiar with where to find things on the VCAA, that's the VCAA website. And one of the things you will find on there for each exam in the past is the assessment report. Now this is, it's both the answers and also a summary about the exam. So the kinds of questions that people did well and the kinds of questions that people did badly. So there are some good points to read here. For example, on this first page, now you might struggle a little bit to read this on the video, but I suggest you look it up yourself. It talks about things like the need for neat handwriting so the assessors can read it in order to give you marks. You need to show your working in order to gain marks even if you get the final answer wrong, and various other things that are useful to know. But the bit that we'll find useful this early on in the year is the answers. So when you look down through the document, you find the answers to each question and some comments about it. So I'm just going to work through all these myself, and we will probably, my answers should agree very well with these. Sometimes I find it useful to look at the assessor's report and to consider the type of answer that the question is looking for, particularly for the ones that are asking you to explain or describe something. Anyway, let's get on with the questions from the 2011 exam. Okay, so let's start to have a look at question 1. Now, this is one of these questions where information relates to the following couple of questions, and you may find that you need to refer back to here when you're looking at the questions on possibly on later pages. So, what we're going to do with these is work through them in the way that I would suggest that you do things in class. So the first thing that I would like to do with this question is I'm going to think about the information that I'm being told in the question, and I'm going to write that down so that I know what I'm talking about. Okay, so we've got some masses. So we've got the mass of the tractor, and of course my stylus is going to play up on me here. Oh, there we go. So we've got a mass there. We've got the mass here of 2,000 kilos, so we've got to think about what we're doing there. We've got an acceleration of 0.5 meters per second. So that's the information that's given in this question. Now, thinking about what's shown in the diagram here, it's going to be a tension question and a Newton's laws question. So we want to have those concepts and those equations in our mind. Okay, what the actual answer they are looking for. What is the magnitude of the net force on the system of the tractor and trailer? So moving to a bit of working space here, so what do we know? We know A equals 0.5 meters per second squared. Now we know mass is the tractor and the trailer, it's 2,500 kilograms. Now we're being asked for a force. Now there's only one equation which gives us what we want here, F equals m times A, not divided, and so it is just 2,500 kilos times 0.5 meters per second, and that gives us 1250 newtons. Now just quickly looking back at the information in the question, we've got 2 significant figures, so I would actually round that to 1,300 newtons to 2 significant figures. Okay, moving on to our next question. What is the tension in the rope connecting the tractor and the trailer? So what we've got to think about here is all the forces that are involved. Now, ignore any retarding friction forces. So this is a bit of information that is in the first part of the question here. Now that means that well, we can ignore any frictional forces. So the only forces on the vehicles are to do with the acceleration. So they are the net forces that are involved. Now we're being asked about the tension on the rope here. Now that means that we're not worried anymore about the mass of the tractor. We're only worried about the force that's being required to pull the trailer. So if we move back to our next page for working here, go back to my blue pen. Whoops. Then what we're doing again is the same equation. It is F equals ma because we're finding the net force, but in this case the mass is the mass of the trailer only, which is 2,000 kilos. A is still 0.5 meters per second squared. So F is 2,000 times 0.5, which is 1,000 newtons. That is my answer there. Now, how far does the tractor move in the first 5 seconds? You'll notice this a lot, that you have a couple of Newton's law questions and then you have a straight line motion question, all of which is pretty much straight out of year 11. So going back to here, what do we know? We've got 0.5 meters per second, and the tractor and trailer start from rest. So there are some things that we know and some things we want to find. How far does the tractor move? So how far means we are trying to find displacement. We are told that the time is 5 seconds. We know that the acceleration is 0.5. And we're also told that it starts from rest, so we've got the initial velocity is 0. So we've got our 4 terms that we can use. Now you need to find the equation which has these 4 terms in it. That equation is, of course, x equals ut plus a half at squared. And we substitute into that. Now this term just becomes 0 plus a half of 0.5 t squared, so we've got 5 squared. Now I'm going to get my calculator out for that one. And what I get is, where's it gone? Turn that into decimal, 6.25 meters. Now again, thinking about significant figures here, it should really be 6.3 meters to 2 significant figures. Okay, so we've gone quickly through about 6 marks, I think. Moving on to the next one. So we now have a circular motion question. We've got some information about now the horizontal path of the bike. Now that's actually important, because it's telling us something about the nature of the motion here. It's telling us that the bike is not going up or down the track, and so that means that the net force up or down the track is 0, so the bike is going exactly the right speed to continue in that circular path. Now that makes our lives easier in a number of ways. So we're also able to ignore retarding friction and things like that. So what this means is that the only force that's acting on the rider, or the net force, sorry, that's acting on the rider is the centripetal force, which is, you know, pushing in to the center of the circle like that. Now this actually is one of the questions later, so we will come back to that. But firstly, what is the magnitude of the net force on the bike and the rider? So moving over, like I've said, we know that the net force is the same as the centripetal force, and of course this is being weird. Sorry, I'll try and edit this junk out. Okay, so we know that the net force is the same as the centripetal force in this case. So centripetal force is given by mv squared over r. Now, sorry, I've actually just jumped ahead here and done exactly the opposite of what I say you should do. Think about what we know first. Well, we know m equals 300 kilos. Now, what else do we know? We know that the radius is 20 meters. and we are also told that the velocity is, or the speed, but that's the same as the velocity in this case, v equals 15 meters per second. So we've got all this information here. Now when you've got mr and v, pretty much the one thing you can calculate from all those pieces of information is the centripetal force. So in any event we end up at this equation. So Fc equals 300 times 15 squared over 20, and again going for the calculator, and what I get is 3375 newtons. Thinking about significant figures here, that is going to be 3400 newtons to two significant figures. Look, we will look at significant figures a lot more throughout the year, and it's important to look at the assessors' reports and see how they answer the question. But certainly to answer it at 3375 with four significant figures would not be right. But yeah, we'll look at it more later on. Okay, what is the correct angle of the banked track theta to achieve this net force? Now, because we know that the rider and the bike are travelling at exactly the right speed for that angle of the track, then all we need to think about is the angle that's formed between Fc or centripetal acceleration and the weight or acceleration due to gravity. So all we've got to do is think about the angle that forms there. So I've got this angle here, theta. Now we already know our centripetal force, so let's just go with that, because we've already got this information. We've got 3375 newtons. Now W equals mg, so that is 300 kilos times 10, because we're in a VCAA exam, which gives us 3000 newtons. So that's definitely wrong. Okay, let me just have a think about this one. Well, it's not definitely wrong, but that just seems a little bit odd because one of them is actually bigger than the other. 15 meters per second, 300 kilos, 300. Nope, that is in fact correct. Okay, so it seems like an odd example because what's actually happening in this case is the centripetal force is greater than the weight force of the rider. Now this is maybe a slightly unusual example, but there's nothing wrong with it. So we just need to go with these numbers. What's going to happen though is that my triangle will actually look more like this if I drew it to scale, because our centripetal force is slightly bigger than our weight force. So our angle theta is just going to be slightly bigger here. Anyway, that was just a little bit of a tangent, but it is good to think about whether your answers seem sensible or not. And especially if they, you get an answer that says that, something is traveling faster than the speed of light, or says that a person weighs more than a planet or something, then you're probably doing something wrong. Okay, so anyway, what do we want to know about this? Well, we've got to do some trig here. Now we've got the opposite and adjacent sides. So tan of theta is the centripetal force over the weight force. So theta is the inverse tan of the centripetal force over the weight force. So in this case, tan -1 of 3375 over 3000 equals. This is where you've got to make sure that you can do these sorts of things on your calculator pretty easily, and we get 48.4 degrees. Now, to two significant figures, which would be a reasonable answer here, we're probably going to round that down to 48 degrees. Okay, so we've got our angle there. Now, that's actually the end of this section. I will work through the next lot of questions and put them up in a separate video. Email me if you've got any questions, and what I'd really like you to do is to work through your answers before class next week, and we can discuss things in class.